Good morning. Welcome to NGSS Physics. We are be going over the conservation of energy today. So pull out a pencil, a paper. If you don't have a calculator, I'd grab one of those as well because you will need one. Today's lesson on conservation of energy you'll find in the online physics book, section 3.4. All right, so let's get started here. Conservation of energy. Okay, it's very similar to the conservation of momentum. In fact, the conservation of momentum comes from the conservation of energy. All conservation laws simply say that whatever you're talking about cannot be created or destroyed. So in this case, energy cannot be created or destroyed. It can only change from one form to another. The two main types of energy are potential energy and kinetic energy. So, although in a system, the kinetic energy or potential energy can change back and forth, the overall energy never ever changes. The total energy before any event must equal the total energy after any event. We can write a simple statement that looks something like this mathematically. If you sum up all the potential energy and all the kinetic energy of all the particles in a system, the total potential and kinetic energy of all of those particles in that system should be equal before and after any event. This takes something into consideration like a stair step. Now remember, the total potential energy and kinetic energy, okay, uh, added together, potential energy plus kinetic energy added together, okay, should equal the same uh, total energy, okay? And a lot of times we call this total mechanical energy. I'm just going to P a T at any step. So in other words, if the potential energy gets bigger, then the kinetic energy gets smaller so that this addition problem is always true, or vice versa. If the potential energy gets smaller, the kinetic energy should get bigger. Notice that there are 5 steps, and it tells us that down here there is 0 potential energy, and up here there is 50 joules of potential energy. This tells me that each step probably is worth about 10 joules of potential energy. So number 1, determine the potential energy at each step. This makes it easy. Subtract 10 and you'll get 40 for A, 30 for B, 20 for C, 10 for D, and then finally the 0 joules at the very bottom that we have for potential energy. Determine the potential energy at F. F is way down here at the bottom right. Well, okay, it's not some height above the ground, and potential energy talks about being above the ground in the gravitational pull. I'm going to say that it is 0 joules of potential energy at F. Number 3, determine the kinetic energy at E. Okay, so the potential energy is actually 0. What is the kinetic energy? Well, if potential energy and kinetic energy always add up to the same number, and up here it was 50 joules potential energy and probably 0 joules of kinetic because it's not moving, I'm going to say it's 50 joules of kinetic energy at E. Number 4, would the velocity of the object at E and F be different or the same? This is an interesting question. Well, if I take a look at my kinetic energy formula, okay, I can see that it is 1/2 mass times velocity squared. They both have the same exact kinetic energy, 50 joules, and they both have the same exact mass, so I'm going to say they have the same exact velocity. Here are the answers. All right, so remember, we've got 2 formulas. You have one for potential energy that talks about its height above the ground, and one for kinetic energy, the energy of motion, that has velocity in it. So if we want to find the final velocity of an object using the energy equations, it's obvious that velocity isn't in the potential energy equation. It's only in the kinetic energy equation. So I'm going to use that one, and I'm going to solve for V. Okay, it's going to look something like this up here, solve for V. And we did this already in lesson 4.2. But what if we don't know the mass? If we don't know the mass of the object, then it makes it very hard to use this equation because you need mass. Um, It just so happens because of the law of conservation of energy, we know that this potential energy at the top should be the same amount of energy at the bottom, but it's all changed into kinetic energy. Can we use that law of conservation of energy to help us? And the answer is yes. If we say that, put those two formulas against each other, the potential energy that you calculate at the height, h, is going to be the same amount of kinetic energy that you calculate that you need at the bottom to calculate the velocity. We can then put those two formulas against each other and make them equal. In other words, potential energy, here it is, mgh, at the top should equal kinetic energy, here it is, at the bottom. Okay, the kinetic energy at the top equals the kinetic energy at the bottom. And so you get mgh at the top equals 1/2 mv squared at the bottom. Notice that m is on both sides, and you can actually cancel them out. Get them out of there. And when you do, all you had left is gh is equal to 1/2 v squared. Now you can solve for v without having mass in it at all. And if we manipulate the formula, we get something that looks like this. Since mass cancels out, okay, it's not a factor when you're finding the final velocity or the height against gravity. Okay, so we could figure out how high it is without knowing the mass if we know the velocity and vice versa. Notice that this is really just the mastery equation without time. So we didn't even really need the energy equations to solve this, if you remember your mastery equation. Just to pause about our equations, you have a formula sheet. And if you don't have it printed out, I would print it out. Let's take a look at where these formulas are on the formula sheet. All right, up here in the force and energy, you have the energy equations. PE is equal to mgh, Ke is 1/2 mv squared. That's where you'll find it on your formula sheet. If you need to solve it for V, because that is kind of a complicated equation, go ahead and write it into your formula sheet. If you need to put them against each other and solve for V or H, go ahead and do that. Here's that master equation that we were talking about. All you have to do is substitute in an h for the x, because now we're not talking about a distance right or left, but a distance above the ground. And then that acceleration, a, should be g, the acceleration due to gravity. And if you start from a zero velocity state, that of course gets x'd out of the formula. And so now it looks more recognizable. Okay, let's take a look at problem number 1. This is a trampoline problem. You've got a skeleton bouncing on a trampoline. If the elastic potential of a trampoline is 100 joules, what is his kinetic energy as he leaves the trampoline? Well, I'm going to say his kinetic energy is 100 joules. Okay, so he gets to the highest point. What is his potential energy at the highest point? Well, you know what? There's a conservation of energy. So I'm going to say his highest point energy is probably 100 joules. If his mass is doubled, would it change the highest point he could reach? Well, let's take a look at this formula for a second. PE is equal to mgh. Okay? So if you take this number and double it, times it by 2, how do you keep the same PE? Well, it looks like you're going to have to half that height because g doesn't change. So I'm going to say 1/2 the height. Okay, here are the answers. 100 joules, 100 joules. Double the mass, you have to half the height. All right, let's take a look at another problem. The first picket in a picket fence is placed 0.15 meters above a photo gate. What velocity do you expect the gate to measure when the first picket passes through? What is a photo gate? A photo gate is just a camera that can measure, here's where the camera would be, and it's like a light sensor that would measure each time one of these pickets goes through. And so knowing the distance between the pickets and the time it takes between them, velocity can be calculated very, very easily. Okay, so if you have a picket fence, and this is called the picket fence because there's like lots of lines, above a photo gate, what velocity do you expect? Well, let's go back and take a look at that formula. If you wrote it down, if you didn't, I would write it down. The one that has the height, because we have a height. Here it is. That's how high it is. Do we have a g? Of course we do. G is the acceleration due to gravity. And hopefully you remember what that is. It's also on your formula sheet at the bottom right-hand side, 9.8 meters per second squared. Plug those numbers into the formula, and you should be able to get the correct answer. All right, let's take a look at another problem. Watermelon problem. Very nice. Problem number 3. Okay, so let's see. A 3-kilogram watermelon sits on a table 1.2 meters above the ground. What's the PE on the top of the table? Well, hopefully you're thinking about, what is my formula for PE? Take a look at the formula for PE. Okay, do you have a height? Yes, I do. Do you have a G? Yes, I do. That's always a constant, 9.8. Do I have an M? Yes, I do. If you plug all those numbers in, you should get the potential energy at the top of the table. What is the kinetic energy as it sits on the table? Well, I'm going to say if it's not moving, remember kinetic energy is the energy of motion, okay, then it has a certain kinetic energy. That's very easy to get, okay? Letter C. What will be its kinetic energy if it falls and hits the floor? Well, remember, there's a conservation of energy. So whatever potential energy it has on the top of the table, as it falls, it loses all of that potential energy until it has 0 on the floor. And all of that potential energy should become kinetic energy. So take a look at your answer for A. And then let's see, if it falls off the table, determine the velocity of the melon right before it hits the ground. Now here we have 2 choices. You can use your velocity, okay, is equal to the square root of your kinetic energy over m, because hopefully you calculated the kinetic energy in A and you have an m up here. Of course, you could also use your velocity is equal to 2gh, okay? Because you know what g is, 9.8, and you have an h right up there. So you have 2 choices here to calculate the velocity of which formula that you want to use. Let's take a look at the answers. Okay, we'll plug in those numbers. Here is my mass, here is my g, here is my h, 35.3 joules. Ke at the top is 0, it's not moving. Okay, what will be its Ke as it falls and hits the floor? Well, we're going to bring that number down because all of that potential energy changes into kinetic energy. And if it falls off the table, determine its velocity. Pick either one of your formulas. Okay, I'm going to pick this one, plug in my numbers, and I should get 4.85. If you choose the other formula, the square root of 2gh, go ahead and try that one, and you should also get 4.85. All right, roller coaster problem here. A roller coaster car starts from point A and goes to point B. And point A is 100 meters above point B. What is the velocity at point B? Well, I'm going to use my formula here, my velocity, because I am given the height and I am not given the mass. There's only one formula I can really use, and that one is 2gh, the square root of 2gh. I know what my height is. I know what my g is. That's a constant. Plug those numbers in. If you're not plugging these numbers into a calculator as you are working through the lesson, you need to. And if you're not getting the same answer that I'm getting, then you need to ask the question, how do I use my calculator? The online calculator is very, very simple. You would push that square root button first, and then 2 times 9.8 times 100. With an equal sign at the end, and you should get the same number that I do. Okay, second to the last problem. Let's say you're on the top of the Empire State Building and you drop a penny. The Empire State Building has a height of 381 meters high. Question, if the penny is dropped, what will its velocity be? Well, we don't have a mass for the penny, okay? But we do know that we can pit those formulas against each other, and then we can end up solving without needing a mass at all, just using this equation. Okay, your answer should be 86.4. Go ahead and plug that number 381 in, and that's what you should get. Looks like I'm going to do it for you. Okay, last problem. A skier with a mass of 45 kilograms is traveling at 5 meters per second at the time she hits a steep hill 10 meters from the base of the mountain. Okay, so the question is, what is her velocity when she reaches the bottom? So remember, all of the energy that she has at the top is going to be completely transferred to kinetic energy at the bottom. But at the top, it seems like she's got two types of energy. She's got potential energy from being 10 meters high, and she's got a little bit of kinetic energy because she's going at 5 meters per second. So the first step in a problem like this would be calculate her current kinetic energy. Okay, use the kinetic energy formula. Look up on your formula sheet. It should be 1/2 mass times velocity squared. Next, calculate her potential energy. Look it up on your formula sheet. You should find potential energy is equal to mgh. And you have her h and you have her m right here. That's the mass, that's the height. For her kinetic energy here was the velocity that you would use. Number 3, what should her total energy be at the bottom? Well, her total energy should be the same as the total energy at the top. So these two added together should give you the total energy, okay, at the top, which is also the total energy at the bottom. And then finally, using her total energy at the bottom of the run, calculate her velocity. And here, you know her mass, so I would use either one of those formulas to calculate her velocity. There is that formula for kinetic energy. Here's potential energy. Okay, add them together, and here you go. Obviously, you can use the square root of 2ke over m. Okay, let's plug those numbers in. In conclusion, okay, energy is not created or destroyed. There is a conservation of energy. Energy can change forms between Ke and Pe, and the total energy must be equal to the starting total energy. The final total energy and the starting energy in any system is always the same. That's the conservation of energy. We can, when energy change forms, we can use our energy equations to calculate the final velocity or the final height just by manipulating those formulas around. Okay, I'll see you in the main classroom. Thanks for listening.